So using the equation that we just discussed before, some trial and error was done. So failure analysis was done using this one-dimensional simple theory. So that formula was plugged onto an Excel spreadsheet and tried some possibilities. So there were two possibilities which were considered. This is the first possibility, and this is the cases 4 to 9. We may term it as the second possibility. So in the first possibility, what was done was, the cohesion of the soil was decreased from 10 kilopascals to 3 kilopascal. Okay, so the first case, the cohesion was 10, and you can see that the safety factor is 1.74. When you have a cohesion of 10 kilopascal, the slope is likely to be stable with a safety factor of 1.74. But when the cohesion was reduced to 3, we can see that the safety factor reduced significantly, and it is only slightly more than 1. So that's the first possibility. The soil would have lost the cohesion. And just to brief upon, the cohesion is generally contributed by all the soils actually. It's contributed by the cementation effect in soil. So this particular soil formation, residual soil formation, has no cementation effect. So if there's no cementation, it loses its cohesion completely. Okay. Then also the cohesion is contributed by, when the ground is unloaded, the ground becomes over consolidated. So it becomes high in cohesion. So yeah, so that's the first possibility. So the cohesion dropped, safety factor dropped. And the second possibility is that the cases from 4 to 9. So what could have happened? Under heavy rainfall, the water table would have risen, and the small h, which is this one, this value, small h is the water table above the failure surface. So when this increases, that is when that water table rises above the failure surface, we can see. So when we increase the h, we can see that the safety factor reduces. And when the h is like 0.9 meter, that is water table is 0.9 meter above the failure surface, means the safety factor is 0.98. The slope will fail in such a scenario. Just to give an idea of the soil formation here. Here at this location, at this project site, the soil formation is called Bukit granite, and it's a residual soil. So residual soils are the original soils below ground, which are formed over millions of years of period of time by weathering of the rock. And this particular Bukit granite formation has a lot of clay. Okay, actually a lot of kaolin material. As we mentioned, the strength of the soil has two components: the friction angle and the cohesion. And in this case of clay, the primary contribution of the strength is from the cohesion, right? As we just mentioned. So, and the friction angle of clay in a fully drained condition can be as low as 21 degrees. Okay, so if there's no cohesion, the strength of that Bukit granite formation or the clay soil is only from the friction angle, which is only 21 degree. So if the cohesion, let's say for instance, the cohesion reduces to 0. So the strength that soil has is only due to this 21 degrees of friction angle. And for the slope stability basics, we may know that the friction angle of the soil, if it is greater than the slope angle, the slope will not fail. The slope will be stable. So here in this case, as we mentioned, the angle of the slope, it's a 1:2 slope, and the angle of the slope is 26.5 degrees Celsius. So if the soil forming that slope is having a friction angle of more than 26.5 degrees Celsius, the slope will be stable. So, but what happens here is, at any particular instance, due to heavy rainfall or whatever reason, if the cohesion reduces to 0 or anything close to 0, the strength of the soil or the resistance against the failure of the slope is only due to the friction of this clay material, which is only 21 degrees Celsius, which is much less than the slope angle of 26.5. This cohesion might have reduced significantly due to various reasons. It may be due to, like, it might have, as we mentioned before, the stress release, and over a period of time, it would have reduced the cohesion, or it could be due to this heavy rainfall and the seepage, and that might have caused the failure. So now we know the probable reasons for which might have caused the failure. Now what we have to do is we have to design a stable slope on site. Okay, So for that, in order to design this permanent stable slope, we used a package called GeoStudio. So GeoStudio is a numerical modeling software package. It has got different programs. They're all integrated to each other. There is Seep W, Sigma W, Slope W, etc., etc. So Seep W is basically used for seepage analysis. It will, for if you're talking about this particular case, if you input rainfall intensity, permeability of the soil, etc., and some other parameters, it will tell us how much volume of water is likely to flow onto the surface of the slope, and it will also calculate the pore water pressure for us. So we can use these information and integrate it to slope W, and we can find out the safety factor against the slope failure. And so, as I mentioned, we used two different programs. One is CW, another one is Slope W. So we tried different combinations of analysis, but in this presentation, I'm just I'm showing only three of them. So what was done was rainfall intensity of 150 mm per hour rainfall was keyed in, and this is CW analysis. It will give us, these are flow nets actually. You can see that the direction of how the water flows and how much water will flow to the surface. As you can see, it is approximately about 3.3 times 10 to the power of -8 meter. The unit will be meter cube per second per meter run into the paper. So this was what we got from CW analysis. And then let's look at the stability of the slope. So this much water is getting onto the surface, slope surface. We know that how much water is flowing onto the surface, infiltrating from the back of the slope when the rain falls from the back of the slope. So this much water is coming onto the slope surface. Now let's see the stability. So stability, the safety factor is only 0.923 for that specific case. Okay, so it's not a stable slope. It will fail because the safety factor is less than 1. So what should we do? We should find some solution in order to make the slope stable. So we previously mentioned about subsoil pipes. So then the next option done was installation of the subsoil pipes. So we can see here, this is a subsoil pipe called GeoNet. It's just a type of subsoil pipe actually. So this was installed at this location, and this length is 4 meter. So the subsoil pipe was installed, and you can see that the flow net, that direction also changed so that most of the water is flowing to the subsoil pipe. Now, if you look at it, the amount of the water that is flowing onto the surface has reduced slightly. Now let's look at, so the subsoil pipe of 4 meter was 4 meter deep into the slope was installed. And let's look at safety factor. Safety factor is approximately 1.3. So the slope is likely to be, it's stable. The safety factor is greater than 1. Now let's increase the length of the subsoil pipe from 4 meter in the previous case to 8 meter. So I hope you can see that it's an 8 meter subsoil pipe into the face of the slope. What we get is a safety factor of 1.6. It's a much more stable slope. Okay, now I have a summary. So as we increase that depth of the subsoil pipe into the face of the slope, what will happen is the rainwater which is infiltrated onto the face of the slope will not reach to the face of the slope, but it will be detoured through the subsoil pipe, and the water flows out into, actually there's a pond just outside the pipe. So as we can see, as the depth of the length increases, the safety factor also increases. So at the end of the day, 15 meter deep pipe was used for the project. And also we can see that after, once you install a 4 meter, 8 meter or 12 meter or 15 meter, the seepage of the water onto the slope surface also reduces a lot. So from 10 raised to -8 meter cube per second, it reduces to 10 raised to -12 meter cube per second, less than 10 raised to -12 meter cube per second. The repair was done panel by panel, and all these fully soaked residual soil that was, slid was completely removed and replaced. and the all the soil that was exposed was recompacted. So yeah, in order to have a stable base, the soil below, just below the planned location of the subsoil pipe was compacted, so that you can place that subsoil pipe on a firm ground. Yeah, and the residual soil was, compacted layer by layer to form that clean slope surface. So in order to conclude, this methodology of using the subsoil pipe was cost effective. It was economically a viable solution for the contractor, and kind of a 15-meter deep subsoil pipe was used as kind of an interceptor for the rain, so as to detour the water, the seepage water, outside of the slope. Oh, okay. So these are some of the pictures from the site, from different angles. So this is a slope that we are talking about. This was the actual location. Actually, it is slightly higher. They cut it down to this level, and this is a slope. It's actually, they constructed a pond here, and you can see that there are these cracks, tension cracks all over. It's quite visible. There's a progressive tension cracks. And finally, this is from another angle, complete collapse of this clay that, as I previously mentioned, this is Bukit granite, a formation called residual soils of Bukit granite. It has got a lot of clay, cohesive, material. So it completely collapsed, losing the cohesion. Yeah, and we can see that the water is completely drenched and soaked. So because of high groundwater table. As I mentioned in the introduction, when the slope failed initially, they tried to, gather some dry soil from same project site and try to dump it, put it layer by layer, compact it layer by layer, but it still failed. So they tried to cover it up. Yeah, so this is a photograph of the pipe. The geotext. Actually, what happens is these pipes has got perforations on the top of it, and it will be, covered with a geotextile wrap on the top, so as to have a drainage so that no soil will seep into the pipe, clogging the flow of the water. So these are pipes with perforations and covered with some kind of geotextile material. And these are 15 meters into the screen. And these are 75 in diameter. They were installed at 1.5 meters interval. So the distance between this and the next pipe would be approximately 1.5 meters. So this is after the completion of the project. So this is the pond that I was talking about, and as you can see that, there's watermark here, right? So these are the locations of this is 1.5 meter, and these are the pipes which is into the slope, 15 meters into the slope, and after the infiltration, water will be carried by the subsoil pipe, and it will be routed to the pond. So we can see quite a clean and stable slope here. Yeah. So with this, we come to the end of the presentation. Thanks to all.